Just a reminder that next week we have an exam on Thursday. Next Tuesday we review. So start thinking of questions you have.
Will coupling and cohesion be on the exam as well?
Yes.
Professor, what about the assignment 2?
I'm slowly working on it. It's taking a long time. Plus I have to, another course is taking a lot of my time right now. List of topics. Basically everything we covered through this week.
What is going MCQs or what?
I was not able to get that.
I'm sorry, I said what is going to be the format of the exam?
By format, you mean is it true, false, or?
Yeah, MCQs, or would there be code like small coding sections or what?
I've not been very successful in asking coding questions in this course. You know, to help grading, I sometimes ask a few questions, true, false. Most of the time it's, you know, ask a question and you write a little, you know, short explanation of the answer.
So, oh, sorry. So what you'll cover today and Thursday will also be on the exam?
Correct.
Can we expect grading of the assignment before exam?
I hope so. Okay. Go through the ritual of sharing my screen. And then I have to rearrange my windows. Okay, now we need list of everyone and chat. Okay, so last time, backing up a bit, remember temporal cohesion, right? So the definition, had this initialization module, and then we had this question, right? And if I remember correctly, no one had any idea or was not willing to venture a guess. And so you were given a small little mini assignment to think about this.
Well, the advantage of having a constructor and destructor, if you're going to do everything at the same time, is that, well, it's just, you don't necessarily, the information on like what you have to do in the beginning is located where where it'll be most like it'll be grouped with the actual class instead of with in this other thing that's calling a bunch of different things. And then just because the temporal cohesion, just because you're doing a bunch of stuff at the beginning, doesn't mean that they're all going to be stopped being used at the same time. And so the destructor will automatically handle getting rid of stuff instead of like destroying everything at the same time or deconstructing everything.
So let me push you a little further. So you said that with the constructor part, I mean, details are going to be in the class. But what do we gain by doing that instead of having one method do it?
Well, if we want to change, if we want to add a new thing, we won't. It'll just be contained, and if we ever want to change the code, it'll just, I don't know, just having it within the object or the class is in general just better, right?
Yeah, so why is it generally better?
I guess it's like kind of a way of turning temporal cohesion into another type of cohesion within more.
Maybe it's better because of the intention, I guess, of the constructor. That the intention is to get the object ready for use. And in that way, you don't have to worry about checking for initialization and all of the other functions and things like that in a class.
Yeah, so let's look at the alternatives, right? So, alternatives, we have, some module that does all initialization, right? And the other alternative is that we do it in the constructor and destructors. So if we have this big method that's doing everything, right? It needs detailed knowledge about almost everything, right? So we got a bunch of objects over here, and a bunch of objects over here, right? Now this method has to know details about this one, details about this one, details about that one, details about that one, right? So this module has to know a great deal of things, right? If we're doing the constructor, right, then then that initialization method becomes much smaller. And now what does it do, right? It only has to call the constructor of the object to create it. And so all the details need to create this object are here now instead of over here. Right, so at some point we're going to have to create all these objects, right, that we still need. But the place that does it needs to know a lot far less. Only needs to know, oh, I need that object, right? I need this object. And we don't have to know what's inside of all these objects. Whereas when we have one big module do all initialization directly, it's coupled to all the details of those objects, right? And we don't want that. We just want to know we need these 10 objects put together in this way. And then each object can deal with its details, right? So the part where we start the program up, you know, the amount of detail you need to know goes way down, right? And it allows you then, right, to change these objects internally without affecting that module, whatever it is that actually starts the thing up in this case. Does that make sense? Okay, now let's, we need to find where we were. And we just looked at talking about cohesion is harder because how do you know when things fit together properly? You know, it's not like a big puzzle where you physically put them together. It's like we need to understand the domain to understand how things are related. You know, so he's trying to figure out, you know, some way of thinking about this to help us out decide when things are cohesive, right? So we talked about this primitive method, right, a composite method, and then, oh, we can look at all these, the smallest number of primitive methods to get the job done, primitive set, right? And the problem with that is made it maybe too difficult to use, or it doesn't give everything we need. And then, you know, you try to come up with this idea of a complete set, right? And then, you know, I went through several examples of different languages. You know, where, you know, in Java, we have this small little set of methods that we implement, right? And then we get all the methods in the collection, right? So here's all the methods we get. Is this a complete set? Now, this is what the Java people thought we needed. You know, the Ruby people wanted far more methods. And the Smalltalk people outdid, you know, both, you know, the Java and the Ruby people combined, what they added to their equivalent collection class, right? So it becomes hard to talk about how big or small is that set. It's going to depend somewhat on your perspective. And now he's trying to use this idea, right, of primitive methods. You know, and he gives, you know, look, it's only primitive methods, but doesn't give you the abstraction you need. It's not good enough. You know, primitive composite methods, but doesn't give everything we need. Not good enough. You know, sufficient set. I mean, again, he's just trying to figure out how we can think about this in terms of what makes a class cohesive. And another idea he talks about are these composite objects. Here it gets a little tricky because by composite object, it doesn't necessarily mean that's actually composed of one or more objects. It's just that it's conceptually composed. What does that mean? Well, if you look at a date object, right, a date object has a year, right, a month, day of the month, maybe a time of day, right? So we can think of a date object as containing different objects, a date object, a year object, day, month object, day of, right? But we can implement, and usually we do, by just giving, one long integer, which represents, how many milliseconds from some time in the past, right? So in Unix, it's 1970 usually. So physically, a data object is just one long number, right, inside. But conceptually, we think of it as a year and a month. And we can ask for, give me the year, give me the month, right? Give me the day, give me the time of day. Right? And so in that case, right, the year and the month are externally discernible because we can ask for it, right? Give me the month, or we can say change a month from October to September. Now he wants to, how can we think about the cohesiveness of a composite object? Well, if those components are not related, then not very cohesive. Some are related is better. The components don't represent a single abstraction, but they make sense in an application. So we're slowly trying to figure out what is it, how can we talk about the cohesiveness of a composite object. Right. Right, so looking at individual objects, we do have all items and objects belong together, methods, minimum session set. Do we have extra application specific items? So assignment 1, right? Examples of a heap class, right? Worrying about odd numbers. That's an example of a application specific item in that class, right? So that's, his struggle with, how can we talk about cohesion? And now we get to some slightly more interesting things. Object coupling. Coupling is just how things are tied together, right? When does one thing reference another thing? How many times does it reference it? How detailed is that referencing? And so even inside of a class, we can talk about the coupling between elements of that class. And so we have to differentiate between, internal coupling and cohesion of an object, right? The cohesion talks about, do all these things belong together? They make sense together. And internal coupling is this, it's the physical relationships, right? If we have a stack, we've got pop and push, and those make sense, right? Those are what define a stack, and we know they're related, right? They belong together. But now when we talk about the physical connection, right, pop and push have to interact with however we're storing the stack internally. So there's a physical connection that they need, right? So that's a form of internal coupling. Right, so interface coupling, right? That sounds good, right? You're talking to the interface. And so there's, a number of ways we can talk about this. So one place this comes up, even in assignment 1, assignment 2, we have a heap, right? And so I have a node, and now that node, what does that node hold? Well, once we specify that it contains an integer, right? We've now coupled that cell to that interface. If we use a template class now, right? Now we can decouple our node from a specific type. Right, so it talks about, assumptions you've made, right? And that first link, this cell, it's making assumptions that we're only hold integers. Whereas the second one, right, we're not making any assumptions about what type of thing it holds, just that it holds a thing. So by selector, it just means, a method that returns information about the object, right? So, one example I use is, say we've got a counter, its counts numbers, the increase, decrease, and now we want to display that information someplace in a GUI. Well, if we, inside my class, right, my counter class, I have some sort of method which displays the screen. Now my counter class is coupled to how to display things to that screen. I can reduce that type of coupling by, say, having a toString method return the value of the count. And now my counter class does not have to worry about how to talk to a particular type of GUI interface. Because it can return a string, and then we can have some other code over here which interacts with the GUI, and our model becomes, in this case, a counter. It's not coupled to that particular type, so it can use that counter elsewhere. Right, so here's my counter class. I got some counter, an increment, and some display method, which does all the work to, display this little this little slider here, but if I add this toString, now I can, in my GUI part of my application, I can ask the counter, instead of saying display, I just say, give me your toString and I'll display it for you. Does that make sense? You talked about iterator. Well, we talked about this. Iterator just allows us to, right? The outside world doesn't have to worry about how internal workings of a class, right? Well, so he considers like these selectors, constructors, and iterators to be primitive methods. By constructors, he just doesn't mean necessarily just a constructor of of the class, and methods which construct a new version of the object, right? Another concept here, the issue is, we talk about we want as loose coupling as possible. Why? Because we want to be able to change things in our system, right? And the less things are coupled, the easier it's going to be. But now, his idea of a primitive object, these are objects which are globally known and defined in the language implementation. And so an example of this is in Java is a string class, right? The string class is defined by, if you look at language definition, it talks about what the string class should be, and it's globally known. And so he says, when we're talking about coupling with other objects, we should not count these primitive objects. And the issue is, why not? This time, someone besides Hong should answer.
Well, I think something that we found in the last assignment was that we couldn't use an integer as like the type. So there's a few restrictions in terms of polymorphism and inheritance and things like that. So I guess to me, it's like the lowest you can go in terms of class features. So that's one reason, I think.
But if we use a string in a class, our class is coupled to a string, right? So why should we not consider that when we're talking about the coupling of that, class A? Why should we not mention strings or ints, right?
Well, if it's in the standard, you have access to it everywhere, so you're not really coupled to it in a sense.
Yeah, Dylan's right. I mean, the idea is, look, if it in Java, there's no way you can run a Java program and not have a string there, right? And so the idea of worrying about coupling is when an object is too coupled to things, we can't move it elsewhere. But if we're just coupled to strings and ints, any Java programs are going to have access to that, so we don't need to worry about that coupling, because wherever we move that class, that object, right, in a different system, Java system, it's going to be always there, right? Of course, it's not 100% correct in the sense of then Java ME came out, micro edition for small spaces. And to make it small, they had to remove a lot of the standard stuff, right? So, but then you have to consider sort of like two separate systems. There's the regular Java E and Java ME. Inside internal coupling. So it used to be a big debate in the early days. You know, so we have a class, and the class has got fields of properties, and now we're going to access those in all our methods. But that's a form of coupling, right? And what happens if we want to, you know, for example, we have a stack class, and there's different ways we can represent that stack. One is an array, another is a linked list. And so we say, oh, it's great because now we put that inside the stack class, and the outside world does not have to know about those changes. So I can change it internally, and we're good. But if every method accesses that stack as a linked list, now I want to change how I represent that stack internally as an array, I have to go and modify all the methods in the stack class. And so some people argue that, oh, one way to deal with that is you have sort of basically private methods that you use to access and set all your fields. So if you ever change how they work, you can do it just by modifying those accessor methods, and the rest of your methods in the class don't have to change, right? You know, I normally don't do this, but years ago, working on a project with someone, and they always did it, and the project we were working on really helped it because it allowed us to do some things quite easily. But also I know, you know, Ralph Johnson, one of the authors of the Gang of Four design patterns book, says, look, it really depends upon how easy is it to refactor your code. What sort of tools do you have? You know, is it easy to take a class that doesn't do this and then create those private accessor methods and then replace all uses of that field with those getters and setters? Then that's easy. Then you can probably not have to worry about doing this. Inside internal coupling from underneath. I mean, yeah, you know, the basic issue is you've got inheritance, so you've got a subclass, and your subclass can access all the fields and the methods. And if they start accessing the fields directly, they may make changes that aren't appropriate. So do you really want your subclasses to interact with your parent fields directly or not? And the other issue is what happens when Your parent class has methods that don't make sense on the child class. And it's, oh, the classic example given there is this fake one where you've got a rectangle class and you subclass it with a square, and then a square doesn't make sense to be able to set the width and height separately because the square has to have them both the same. Outside internal coupling from the side. You know, we can access the private state operations of another class. You know, people like to beat up C++ for that because they got friends, but you know, you can do the same thing in Java with reflection. So the whole idea of talking about coupling and cohesion is to help you think about how tied together your system is, right? You know, one of the things that people say is good about object-oriented programming is code reuse, right? And usually by code reuse means we can take this object here, this class here, and move it over here and use it else in a different program. But for that to happen, we have to think about, right, how is the object coupled to other things? Because if it's coupled to other things, when you move it, we have to drag those other things too. And if that the net of things which are coupled together gets too big, then when you pull one thing out, we get this huge graph, right? And it's also helps you think about if they're two coupled together, then making changes here propagates. And think about, you know, does this object represent a good abstraction or not? Are there things missing? So it's just a way of setting, you know, stepping back from your code and giving you another way of thinking about the quality of the system you're dealing with. Does that make sense? Now, once I talk about coupling cohesion as talking about quality of code, that leads us to metrics. And when we talk about metrics, we have to keep in mind DeMarco's principle. Effort moves toward whatever is measured. And this Dilbert cartoon illustrates DeMarco's principle very well, right? So the pointy-haired boss, you know, okay, we want to write bug-free code, and so I'm going to pay you, you know, $10 for every bug you find and fix. And all the developers are quite happy because it's like, well, as Wally says in the last panel, he's going to write a minivan this afternoon, right? So if you're going to pay me to fix bugs, I will write as many bugs as I can, and then I'll fix them. And so I'll get paid twice, right? You're going to pay me a regular salary to write all these bugs, and then you're going to pay me $10 per bug to fix them. The goal of using metrics is to help us gain some insight of what's going on, either right now or over time. and try and help us understand how we can improve. But the Markov principle shows that we have to be very careful about the metrics and how we use them. They'll drive us to non-productive behavior. Another one to keep in mind is, if the map and the territory don't agree, you go someplace and the map says there should be a road going there, and there's no road going there. Don't believe the map, right? And the same thing with metrics. You have to be careful. Metrics aren't perfect. And I've talked to people who've been on projects that were basically falling apart about the collapse, but all the paperwork and all of it made it look like it was going on schedule, on time, and everyone in the project knew it was never going to get completed. The way behind schedule, things were in terrible shape. So when we're talking about metrics, you always have to keep both these two things in mind. So there's Eclipse is getting pretty old in the tooth. There was a package for it which would generate a bunch of metrics, which made it nice. There's another version which generates most of the same metrics. So one metric, just to talk about the size of a project, is lines of code. And part of the motivation is that the effort needed is correlated with the number of lines of code. Now you have to be careful because different languages are more verbose than others, right? So Java is fairly verbose. Kotlin, which compiles down the Java code, is not verbose. So you can do, given two tasks, usually the Kotlin code is going to be much shorter than the Java code, doing exactly the same thing. So most of you don't worry about this because you're probably not managers. But if you're going to bid on a contract, so for example, there's a fair amount of military work done in San Diego. And there what you do is you bid on a contract to say, we'll do this contract for a fixed number of dollars, right? So any contract work, you want to know how long it's going to take, how many resources do we need. And so there's a couple of models that were used to try and estimate the cost of software based upon the number of lines of code. And so here is the sort of basic model where it's A times kilolines of source code raised to the B power. But the question is, how do we fit A and B? And so it really depends on what types of projects you're working on, the language you're using, and the team. And so they estimated various values of different types of teams. But if you take a software engineering course, they should talk about the COCOMO model particularly San Diego State. And there the idea is that the team would track their projects over time and refine the values of A and B to make it easier to, once you estimate how long the source code is going to be, then you can estimate how much time it's going to take. Right, so if you think it's going to take 2,000 lines of code, it's an embedded system, right, then we're looking at, the model says 8.3 man months. Like I said, there's different languages, have differences. Some programmers more efficient than others. Some write smaller code, do the same thing. And also, usually design and debugging and testing take a considerable amount of time. But again, those things are also somewhat tied to how big the project is. All right, so this is one common metric that people talk about. So for these metrics, I downloaded a Twitter client written in Java. And so, here are the results. We're looking at lines of code in the packages. Now I better change color. Right, and then it starts computing how many lines of code in each package. Right, the average per method. Right, and so you look at this, right? Oh, the maximum. So someplace in there, there's a method which is 518 lines long. And I don't know you, that really stands out as way too big. And so of course one has to go and look at it, see what's going on there. And I did, and it's basically, if I remember correctly, it's just doing GUI code. So it's building a huge window with lots of buttons, etc. That's why it's so long. Examples, the mean is getting pretty big. So you look there, and again, it's initial examples made it big. Right, and so that the way you want to use these metrics is to, find anomalies like this and see what's going on. The problem is, as soon as you start keeping track of lines of code, there's a temptation to either use that metric to evaluate people's performance, which is not what you're going to do, because some things are complicated, take lots of code. Other things may be complicated but don't take very much code, and so it takes a long time to get them working, but you're not writing much code. Also, there are times when you built a project up and refactor it and the code size goes down because you're finding abstractions you can use to simplify the project and make it use less code. And if managers start giving out bonuses because the number of lines of code you've written, you'll find, like Rolly, that people will start writing lots and lots of lines of code even when they don't need to, which will not help the project. Another way of looking at it, graphically, lines of code in a method. Right, so we're seeing there are lots of methods which are very short, 2 or 3 lines, right? And then there's another big, around 12, sort of builds up and goes down. On this metric, right, it's sort of coloring all the red ones, indicating that perhaps these are a bit longer than they should be. That doesn't mean they are, but again, it's just a way of saying, oh, maybe you want to go look at some of these and see what's going on. What's a line of code, right? And this statement often can span multiple lines, that might be called multiple times. So just a number of statements per method, right? And now we're seeing, right, between 4 and 5 statements. And then it declines quite a bit after that. That sort of indicates that some of these, right, have single statements that span multiple lines. So it may be that the number of statements per method might be a better metric to use. So number of packages, number of interfaces, number of classes per package. And again, just metrics we can look at. Here again, these are still in the Java Twitter client. But we all know that, some code may be long, but it's quite straightforward, right? You do this, 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 and we're done. Other piece of code may not be shorter, but they're more complicated, hard to understand. So the McCabe cyclomatic complexity metric is an attempt to measure how complicated the code is. And it's basically the number of linear independent paths through your program. And the metric comes from graph theory. How many independent paths are there, linear independent paths through a graph? And it's the number of edges minus number of nodes plus twice the number of connected components. So how do we apply this to code? So a simple example, I have 2 if statements, one after the other, but each if statement represents a branch, right? So I can represent this code as a graph in the middle, where we start, and then we give you if case or else case. We go back, no choice, and we get to the second if statement. And so now we have a graph, right, with 7 nodes. Let's see, 1, 2, 3, 4, 5, 6, 7, right? And again, there's 4 edges. And so we can use, the formula, basically say the complexity, okay, complexity of this code is 3. Clear enough?
So this 3 is just by like plugging in this equation, right?
Correct.
It's because aren't there 4
There are-
linearly independent paths through the program?
There are 4 paths, right? Yes. But they're not linearly independent.
Okay.
Because with given 3 of those paths, I can construct by adding and subtracting, the other 3 paths, I can get to the 4th path. Right, so for example, what are the 4 paths, right? One is, let me erase all this so we can start scratch. So one path is this, like this, right? And then we're going to need another color. Here's another path, right? And let's see, this color will work. Another one is to go like that, right? So those are 3 paths, but there's one more that we want, right? So what we want, how can we construct the other path, right? So the path we want to construct now is this red one. It goes here, that way, and that way, right? Well, let's call this path A and B and C, right? So if we start with B, that gives me the first part of A, right? But we don't want the last part of right, of B. So if you subtract off C, right, that's going to get rid of the bottom part of it, of B. But now we have, we've got a negative value for the top part of C. So if I now add A, what do I get? Well, this minus C and A cancel each other out, so those aren't there. So the first top of B is here, so we get the first part, right? Subtracting out C from B gets rid of this piece, and so that's gone now. Now when we add A, that adds this piece, right? So now we get that part of A, right? So we only need 3 of those paths. We generate the other one. And the basic idea is, go ahead.
No, I was just saying, okay. Yeah, I understand.
So the basic idea is the more branching we do, right, the larger this M is going to get. So the larger M is indicates that there's more paths, linearly independent paths, and the more linearly independent paths there are, indication that it's more complex, right? And now what it does tell us, right, is that, right, as we point out, the number of paths is larger or equal to, right, cyclomatic complexity. But we can, if we do it correctly and our testing covers that many paths, we should cover all the paths. all the path pieces, right? But we're not going to cover all the paths themselves. And so, one study indicated that right, the systematic complexity is a better indicator of cohesion. The lower it is, right? And there's also some studies done that show that the higher this complexity is, right, we get more bugs. Why? Because as the number gets larger and larger and larger, there's more paths to go through, and it's going to be harder to test all those paths. Some of them won't get tested, and if they're not tested, they can have bugs. So interestingly, the National Institute the TSAN for technology, and they basically said, 10 is sort of a danger number. So if you get complexity higher than 10, you might want to think about breaking it up. So here is, again, measuring K systematic complexity on the Twitter client. And here, right, we have an example of the mean complexity of each method is 12, which is above that 10. And here we find there's one with 46. Right, so again, it's just one of these things where the idea is how we want to use these metrics is to point out anomalies like this, and we can go, in theory, look at them and see whether or not they make sense or not. Or should they refactor this code?
Sorry, that's not something I can do.
Right, again, definitely looking at it, clearly there's methods which have no branching, a lot of them mainly. Run this metric, right, it says 5 or greater you should look at. Another metric is, how many methods per class. Again, this is like 235 methods in a class. Seems rather high, so you may want to start looking at them. So various methods people look at, methods per class, study methods per class, fields per class, parameters per method. So number of methods per class, number of parameters. And again, we're getting This Twitter for J package has quite a few anomalies. Nested blocks. I start to get nervous when my nesting becomes 2. When it becomes 3, beads of sweat start forming on my forehead. And I try and do something about it. Come across 4, it's like, oh, no, you don't want to do that. Right? The more nested your code gets, the harder it is to figure, easier it is to lose track of what exactly going on and miss cases. Right? So the tools, generate how many nested blocks there are. That's scary, having blocks of 8. Inheritance, how deep is the inheritance tree? Number of children each, right, the class has, how many overridden methods. So here's an attempt to try and measure the cohesion of methods. So methods define how many methods define the class, right? How many fields are in a class, right? R of F is the number of methods that access the field F, right? And then we take the average of all that. And then, right, here is the formula they want to use. So what happens, how can we make sense of this equation? Well, if each method accesses every field, then this average is equal to M, the size of M, right? And this becomes 0. So the idea that the lower this number is, the more cohesive it is. Again, there's some measurements creating this. This idea of stable code. Only got 2 minutes. I already bored everyone with metrics here and there. So we'll stop here and start up next time. You're slightly alert and
Are we going to be covering more than just metrics tomorrow? Or sorry, on Thursday?
I haven't decided. There's only a few more metrics to cover, right? So it'll take us like 15 minutes.
Okay. And so will the next thing be another
Pattern.
pattern? Yeah.
Now, post that tomorrow morning, if not
Right.
tonight.
Thank you.
Okay, we'll see everyone, or some of you, on Thursday.
Have a good night. Thank you.
Thank you.
Thank you.